We have made it to queues, yet another abstract data type. They are not built up into the core feature set of Java. This is a data structure that we want to build. We want to define their behavior. So what is a queue? A queue is a data structure that stores information in the form of a typical waiting line. So new items, they're added at the end of the queue, and then elements are removed from the front of the queue. So unlike a stack, a queue is actually accessible from both ends, and that's super important to remember. So whereas a stack, we only needed that one reference top, now for the queue, we need to keep access to both ends of our queue. What is the access policy? The first element inserted into the queue, insert into the waiting line, should be, in theory, the first element that we will remove from that line. So in order for the last element to leave the queue, it of course has to wait until all of the elements in front of it have also left the queue. This is known as the first in, first out access policy. The first item into the queue is going to be the first element out of the queue. Simple example in real life of what a queue is waiting to be served in line. When a customer arrives, they enter the end of the line, that back of the line, and they keep waiting and waiting until they arrive at the front. Finally, they arrive at the front, they get their food. If you're in like some checkout line, they get their food and then they exit the queue. Basic operations on a queue are similar to that of a stack. There's historical or classical names. For a stack, we have what? Pop, push. Or here on a queue, we have enqueue and dequeue. Enqueue inserts an element at the end of the queue. This is your insertion method, your insertion operation. It's called enqueue. In theory, this is an O of one time. In practice, dependent on the implementation, it could be much slower. Dequeue is our removal. This is when we remove an element from our queue. Also, in theory, it should be O of one time, but again, depending on the implementation under the hood, it could be slower. Peek, similar to stacks, is merely peeking or looking at the element at the front of the queue without actually removing it. That also should be an O of one operation. We have is empty to check whether or not the given queue is empty. That should be O of one in theory. Is full checks to see if the queue is full. Based off of the implementation, this may or may not be important. If you have an array-based implementation of a queue, of course you need to make sure the array is not full. On a linked list implementation of the queue, this should be less of an issue. It should be O of one time. We also have an operation called clear to clear the queue. What this means is when you have maybe 50 elements in the queue, but then the store closes. You have people in line, they've made it in the store, but now the closing hour has arrived. Well, they're going to lock that door, no one else can enter, but everyone that's currently inside the store ordering their food, waiting in the queue in line, they will be cleared out and they will receive their food and then leave. The running time here is going to be O of n, where n is the number of elements that are currently in the queue when we actually perform that clear operation. So what I'd like to do in the next few slides is cover just the overall nature of a queue and understand this access policy. Clearly, it should make sense to us. It's just a waiting line, but still, it's good to get a visual along with this word of first in, first out. So here we have a queue. We currently have elements inside the queue. We have 5 of them. The element at the front of the queue is 2. Then we have 4, 6, 8. And that last element currently in the queue is 10. What's going to follow are these 5 operations. We're going to do an enqueue, then a dequeue, then 2 more enqueues, and then a dequeue. So here we do our first enqueue of 12. Notice 12 goes at the end. Pretty straightforward, right? Nothing really complicated. We now do a dequeue. So therefore, at time 2, we do a dequeue. So this 2 that's at the front of the queue gets dequeued, and then everything is, the remainder of the queue is as you see. We then do enqueue 14 right here. So 14 goes at the end of the queue. Enqueue 16, 16 goes at the end of the queue. And then finally, we have one more operation, a dequeue, and this 4 will get dequeued, and now 6 is at the front of the queue. Pretty straightforward, right? So now the question is, how do we implement this queue? Turns out there's a variety of implementations. The two we're going to look at are going to be an array-based implementation and a linked list implementation. The same thing that we have previously already seen with stacks. And we're going to go over both of these. With this array-based implementation, we're going to implement that queue as an array. And what does that mean? It means that when we look under the hood, as I say, when we actually look at the code of our class that we're creating for this queue, we find just a regular old array. Pretty straightforward. So then how is it that that array becomes a queue? What makes it become a queue? Remember, we define an abstract data type based off of their behavior. So what makes this array become a queue? The behavior. And we're going to restrict the behavior of this array the same way we did for stacks. And we're going to say you can no longer insert anywhere into this array. You can no longer delete from wherever you want on this array. Rather, we're only going to allow insertions into the array at the back, wherever we define back to be, at the back of the queue. And we're only going to allow deletions from this array from the front. Once again, wherever we define those two locations. So we're going to restrict the behavior of the array, thereby making the array behave like a queue. So once again, with an array, you can insert anywhere or delete anywhere, right? But since we're going to make this array behave like a queue, we only will allow insertions at the back, and we will only allow deletions from the front, which will be our enqueue and our dequeue operations. So now we have effectively transformed this array into a queue. So how would you implement this queue as an array? Or think of the stuff that you would need to actually implement this queue as an array. Of course, we need the actual array. I said you look under the hood, you're going to see an array. But what else do you need? In order to support that enqueue operation and that dequeue operation, we mentioned that you need to know where is the front and where is the back. So we're going to need to have two variables called front and back, just simply storing the index of where that front item is going to be housed or found and where that rear or that back item is going to be found. So here is our class, QArray. Notice we're looking now under the hood. What do we see? We see just an array of integers. This could have been an array of strings, an array of objects, but just to keep this example simple, we have here an array of integer values, and we have a front and we have a rear, the two indices that we're going to use to keep track of the values and their locations. Notice I say that the rear is not actually needed. We'll come up to that and cover that in a bit of why that won't be needed. But for now, let's assume that it is actually needed. I'd like to cover the brute force method. What is brute force? Meaning we're not even thinking about the optimal way of enqueuing and dequeuing. We're just going to show what makes sense, but it might be super slow. That's why it's called brute force. We might be doing a lot of running time here. Let's not worry about that at the moment. Let's just understand what's going on with our front and our rear values. So now we have another sequence of operations. We're going to do one dequeue, followed by an enqueue, followed by all these other 5 dequeues. And let's keep track of front and rear and see what happens here. So first we do a dequeue. So when we do a dequeue, we can see that 2.d got dequeued, and then all of the other items moved left 1 position. Now we do an enqueue, so 12 got enqueued at the end. And now we do another dequeue right here. And I say, notice that the array has still room. We can still add one more element here before we did this last dequeue. We can still add another enqueue, and you'll see why that's important in a bit. So now we do another dequeue, another dequeue, another dequeue, and 2 more dequeues. Here we do dequeue of the 10, and we dequeue the 12. But it's important to see that what happened here, every time we did a dequeue, all of the items shifted over to the left. Yeah, that's that S word. And we had to change the position of rear, right? At time 3, we did this dequeue. Now at time 4, we do another dequeue. So 8, 10, and 12 shifted to the left. And of course, rear changed. Front is never changing, but rear is changing, and everything is shifting over, which is going to be a super, super slow operation. So what's wrong with this actual example? The NQs are all running super fast, O of one time, right? We add a new one, it immediately goes at the end of that, the next available position in that array. So it's super fast. But look at the DQ. The DQ itself, being able to access that first item and remove it, that is O of one, right? That's super fast. However, after that item is removed, all of the other items to the right of it had to shift over one position, which we already know is a super slow operation. We have n elements that have to shift over one position. So therefore, your DQ in of itself, the total running time is O of n due to the fact that all of the other remaining elements in that queue have to then shift over. That's not acceptable, especially when we know in theory we said a DQ should be O of 1, but with this particular brute force implementation, the DQ results in an O of n operation. How can we do better? We want to avoid shifting. In fact, no shifting should occur. So now you have to think, well, if we can't do any shifting, but we need to fix this and we need to somehow get it faster, what's the only option? If we're not going to move the individual elements, what must we do? We're going to move the front and the back pointers. Now, in the last example, we were moving the rear pointer, right? That back pointer, whenever we did a new NQ. But on the DQ, that front index kept staying at index 0 and we were shifting. So instead of shifting everything over, now we're going to actually move the front. And an example will clarify. So the same exact example with these same 7 operations. Let's do a DQ. Look what happens. Nothing shifted. But this time we simply updated where front pointed to, right? We do another NQ. So now we NQ at the end and our queue appears full. Although it's not full, we can see at the beginning we really have some space. But at the right side, at the end of the queue, there's really no more space, which is a bummer. So I say, notice how the queue appears to be full, even though there are, in fact, empty locations within this array. We do another DQ. So front simply increments, but the items themselves are not shipping. So they're not shifting over. We don't have that O of n operation. Instead, front is the only thing that is moving. That index value stored inside front. Another DQ, and we have 2 more DQs. But look at this scenario at the end. Here, we have no values inside our queue at all. The queue is empty, yet it also appears full because rear is on the right side and we can no longer add any elements. So we have a huge improvement. The improvement being what? That we're no longer shifting upon doing a DQ. Huge. We're moving front instead. But now we get this silly scenario where we have no elements in the queue, yet the queue appears full because rear is all the way on the right side of the queue. So we end up with wasted cells. So as the front moves towards the rear, whenever we have those DQs, we end up with these wasted, empty, useless cells in the array. So the benefit is we avoided those end shifting that was occurring. We avoided those end shifts, those end moves whenever we did a DQ, and we did so by simply moving front to the right and incrementing front with every DQ. But in the process, we have wasted space. I ask, how can we do better, or can we do better? Of course we can. And the answer is by viewing the array as if it were circular. What do we mean? A circular array? What? This is a very common implementation of an array-based queue. What is a circular array? In short, it's just a regular array, but we view it as being a circle. In a circular implementation, the queue is considered to be full whenever the front of the queue immediately precedes the rear of the queue in a counterclockwise direction. That's a mouthful. It will make sense once we see and we go through an example. So I'm going to show you that same example again, and I'm going to let you get this visual of what is a circular array. So here we have the normal array implementation. We can see that the queue is completely full. Here is that circular array implementation where we have the array and we've basically taken this end of the array and this end of the array, and imagine instead of being like one solid rectangular structure, imagine each of those cells were flexible. So when I grab the 4 and I grab the 8 and I raise them up, the 2, 15, 11, 10, and 6, they kind of drop down, and I raise the 4 and the 8, and I then tape them together or glue them together, and here's the result. So we have 4, 2, 15, 11, 4, 2, 15, 11, 10, 6, 8. We go in that clockwise direction, and we have this exact same array, but now we're viewing it as a circle. And here's what's weird. As soon as we're done viewing it as a circle, I'm going to say what? I'm going to say, well, now let's cut it. Pretend we have a pair of scissors, and we cut this circular array right here between the 10 and the 11. And you're like, we just went from a rectangular looking array. You got me to wrap my mind around this circular array. Now you want me to cut it and go back to a rectangular array? And yes, the answer is yes. Why? Just to demonstrate, it doesn't matter where the front officially is or where the rear is, because as long as we recognize that we can just wrap around this array. So imagine I cut it right here, and then I grab this 11 cell of the array, and I grab this cell with the 10, and I stretch them back out, and I bring the 11 over here, and I bring the 10 over here. It doesn't matter, because now if I say 4, 2, 15, 11, 4, 2, 15, 11, and we wrap around, so 4, 2, 15, 11, and then we come all the way back to the front, 10, 6, 8. 4, 2, 15, 11, pretend it's a circle, 10, 6, 8. 4, 2, 15, 11, 10, 6, 8. That's exactly what we're going to do on the following example. So a circular array is just a regular array, but we're now viewing it and visualizing it as a circle and realizing that we can just wrap around that array. So it allows us to keep the elements in their respective cells of the array, so we're not going to do any shifting, but we also will not have any wasted space at all. The circular view of the array allows us to wrap around the entire array. We're going to assume the length of the array is called size, which we don't really need in Java because we can always get the length of the array just by the name of the array .length. But we'll assume the name or the length of the array is called size. It's important to know that the rear does not have to stop at index size -1 because we're wrapping around, right? Since the array we're going to be wrapping around with our NQs, that rear could be at index 0. It could be at index 1 or 2 or 3, as we just saw on this last example right here. Here, the rear was at index 2, right? It wrapped around. Then we have 10 at index 0, the 6 at index 1. The rear was actually at index 2 because of the wraparound. The next several slides, we're going to go over that same exact example, and we're going to show the circular array-based implementation of a queue. Next to it, we're also going to show the brute force implementation with the shifting to see them side by side. The brute force is super, super slow because of all that shifting that occurs. So I say here the scenario begins. At some point in time, we've already done many NQ operations. We already have values inside the array. And now we're going to begin by NQing more elements and then dequeuing elements into the array. So here we go. This is our array, 2, 4, 8. This is a normal, traditional looking array. Here is the NQ operation. We're going to NQ the 6. It comes right here at the end. Pretty straightforward. Here we have our circular array implementation. It's just a visual, right? Where now we have the front right here, and we're NQing the 6 right here. And now we want to show you that same circular array, but this time as if we just sliced it. And we sliced it right here. Right here is the slice. And so now we're just showing that same circular array, but now as a rectangle. We want to insert or NQ the 6, and the 6 comes right at the end. So here's the brute force implementation, which we didn't have any shifting yet because we only did an NQ, not a DQ. Here's the circular array implementation where we NQ to 6, and this is also the circular array implementation where we're just letting the front be something other than index 0. Now we have another NQ operation. We NQ a 10, so the 10 simply comes at the next available spot. Here for the circular array implementation, the 10 once again comes to the next spot. Well, look at what happens here when we have this circular array implementation. Well, the 10 comes after the 6 as we saw, right? The 10 comes immediately after the 6. Well, the 6 is already at the last index of the array. No problem. We simply wrap around and we insert or we NQ that 10 at the next spot wrapping around. So begin to think about how you would actually implement this. So that was an NQ. We now have a DQ. So the DQ on the brute force implementation is all of this is going to get shifted over. Super, super slow. Well, here the DQ is the 2 simply going to be DQ'd and we're going to update the front. And what happens here, this is also the circular array implementation. So this is really just for the visual, but we're now, as I said, here we have that same circular array where we've sliced it right here between the 6 and the 10. And so now we have 2, 4, 8, 6, 10, and we're doing a DQ. So the 2 is going to get removed and the front is going to change where it points to. It points now to the 4. Pretty straightforward. Let's do another NQ. We NQ the 18 at the next spot. Here the 18 comes after the 10. Where does the 18 get NQ'd now? Which index, pause the video and ask yourself, which index does this 18 get NQ'd into? The answer is it gets NQ'd right after the 10 at index 1. We have another DQ. So now on the brute force implementation, we have all of that shifting, super slow. We do a DQ here on the circular array implementation. So simply the 4 is removed and the front changes where it's pointing to. Here we have that same circular array implementation. The front changes where it points to and that 4 is removed. We have another DQ, everything shifts over. The front points over here in the circular array implementation now to the 6 because the 8 is gone. So the 8 was right here, it's gone, front comes to the 6. And here's that circular array implementation, but now as a one-dimensional visual. And the front is going to point to the 6 and the 8 is removed. This is after the DQ. A couple more. We have another DQ. The 6 is removed. All elements have to shift over on the brute force implementation. Here's the circular array implementation. And here's that circular array. Pay attention now. Front is currently pointing to the last index of the array. So when I DQ front, that 6 is removed. But now where does front go to? Front is going to come point over to index 0 because we had 6, 10, 18, right? We had 6, 10, 18. But once I remove the 6, we only have 10, 18, which means the front would be right there at index 0. So again, think of how you would actually implement this. We have another DQ, or no, now we're doing an NQ. We NQ a 9. So the 9 comes right here at the next rear position. The NQ of the 9 and the rear changes its index. We have a DQ. So the front is going to become index 1. The 10 is DQ'd. We have another DQ. The 18 is removed. And now front and rear both point to index 9. And we have one more DQ and the Q is empty. So this works great in pictures, but let's actually think about this. How did we modify the position, the index of front and rear on that last example? Did we just increment those indices constantly every single time we did an NQ? Did we always just increment front, or did we always increment rear whenever we did a DQ? And the answer is no, we did not just do that. With the normal array implementation, that would work. But with a circular array implementation, we have to pay attention. There's more involved because simply incrementing will not cut it. So how did we modify those positions of the front and the rear index? Consider this situation here. This is from page 34 previously. If we have the front at the last index, and let's count this over. We have 0, index 1, index 2, 3, 4, 5, 6. So we have the front variable is currently storing a value at index 6, and the rear is at index 1. So we have the value 6 at index 6, and then we have the value 18 at index 1, which is the rear. If we do a DQ right now, when we do a DQ, what happens? This 6 will ultimately get sent back. Imagine we're going to call some method DQ. The result is that method will send back, will return the value 6 that was DQ'd, but also during the DQ, this front has to change, and now it will point to index 0, where that 10 is. So how did we make that happen? Clearly, we did not just increment the front, right? Because front, if we increment it, it will now go to index 7, which would be out of bounds. One solution would be to use an if-else statement. If the front is currently equal to the length of the queue minus 1, if that's the case, that means we're at the last available position. So what's the length of this entire array right here? Again, it's 1, 2, 3, 4, 5, 6, 7. The length is 7. So if the front is equal to the length, 7 minus 1, so 7 minus 1 is 6. If the front is currently at index 6, this means the front is currently at the last cell of the array. And if we're going to perform a DQ, clearly the front, we can't just increment it to index 7 because there is no index 7, right? So now if we perform a DQ, the new front index must be set to index 0. Else, if the front was not currently equal to q.length minus 1, we simply increment the index front. Either way, we then return the value. So let's look at the actual code and make sense of it here. So we have our public int DQ. The return type is integer because we're going to return the value we're DQing. The first line of code, we make a temp value of type integer where we're going to save the value that is currently in that front position of our queue. So go to the array queue, take the value at index front, and we save it into temp. And ultimately, if you notice the very last line of code of this method, we return temp. We return that value that we temporarily saved. Now, why did we do that? Is because we're going to update where our front points to, because it's a DQ, right? So now we say, if front equal q.length minus 1, set front equal to 0. So set the new front to be 0 to take care of that wraparound. But else, if our front was not already at the end of the array, just increment front. So hypothetically, imagine 0, index 1, index 2, index 3. Imagine front was right here in index 3, and we do a DQ. Well, then now front will be index 4. If we do another DQ, front will be index 5. So we're merely going to increment front. If we do another DQ, front will be index 6. But if we do another DQ, front can't just become index 7. Now we have to take care of wraparound, which is what this if statement does. We say if the front is equal to the length of the queue minus 1, that means that the front was already the last cell of the array. Take care of wraparound and make the front now come all the way back to the beginning at index 0. Else, we simply increment front, and then we return our temp. This code works perfectly. You don't need to change this code. You do not need to use the code that I'm about to show you. But I want to show you what we'll also almost historically see in every textbook. And it's cool because this is a little bit slow here because it uses a branching operation. Branching is where you have that if-else, that selection. If we've ever had this situation, bring front to index 0, else increment front. That branching operation is a bit slow, and textbooks instead usually use something a bit different. Instead of using an if-else calculation or an if-else statement to recalculate that position of front, consider if we did the following instead, which is super funky when you first see it. But just check it out. Front equals front plus 1 mod the queue length. So here, what is the length of this queue? The answer was 7, right? We already counted it. So imagine that the front was right here, which is index 0, 1, 2, 3. So imagine the front is currently at index 3. And now we know if we do a DQ, the next front will be index 4. Well, does that work with this equation? We'll check it out. 3 plus 1 is 4. 4 mod the length of the queue, which is 7, is still going to give you 4. So the next front will be 4. And if we did it again, 4 plus 1, 5. 5 mod 7 will give you 5. But now check it out here. What about when front is already equal to 6? Well, take 6 plus 1 is 7, and 7 mod the length of the queue, which is 7, 7 mod 7. Now it brings front back to 0. So this one line of code, it actually takes care of those 4 lines of code with that if and that else. And it takes care of all of the options for us. And so we simply use mod. We increment front, and then we mod it by the size of our queue. And here is the code. So instead of using an if-else statement, we can actually just use mod. So we have this one line of code right here where we're updating our front. Whereas if I go back to where we were previously, to update the front, we required 4 lines of code. We said if the front is equal to the length of the queue minus 1, set front to 0, else we increment our front. But now if we use mod in this intelligent fashion, we can see here we have one line of code that updates our front. And do notice that now on this particular version of the code, I've included this variable num items, and I have decremented it, showing that I'm removing an item from our queue. Why do we need num items, and why is that valuable? We're going to see right now when we look at the enqueue operation. It turns out for an enqueue, we always enqueue at the end of the queue, right? At that rear index. Well, it turns out we don't even need to save that location of that rear index. Why? Because if we know where front is, and we also know how many items are stored in our queue, the number of elements, we can quickly determine the new enqueue location. So here's a simple one. I'm smiling because many students mess this one up. Not meant to be challenging, but just visualize it. Draw out a picture of an array if you have to. Assume that the front was at index 7 and that we currently have 2 items in our queue. Front is index 7. Imagine our queue is infinite in length. Don't worry about the rear. Don't worry about like where it would be located. But the front is index 7, and we currently have 2 elements in our queue. When we go to enqueue another value, which index will we be enqueuing at? Pause the video, think about that. When we do our very next enqueue, which index will we enqueue at? And the answer is 9. Because if we have the front at index 7, and we only have 2 items, that means the first item is at index 7, the next item is at index 8, therefore the next item that needs to get inserted or enqueued into our queue would go at index 9. So we see that the new enqueue position is simply found by adding the index of front plus the number of the elements. So the front was index 7. We have 2 elements in the queue currently. 7 plus 2 is 9, and that will give you the index of the new enqueue position. But we need to take care of wraparound. So assume we have a queue of size 10 from index 0 to 9. The front is currently at index 4, and there are 6 elements already in the queue. So this is what we have. We have a queue of size 10 from 0 all the way to 9. The front is at index 4, so 0, 1, 2, 3, 4. Here's front, and we already have 6 elements in our queue. The next operation is we want to enqueue, and let's say we're enqueuing the actual char G, right? So the enqueue method is a method that we need to write. This G is going to be sent over and saved inside a variable called val, for example. We know that the next enqueue must go right here at index 0. But how do we make that happen, right? One solution would be a simple if-else statement. Once again, it's slow, but we could use an if-else statement. If the front, which is index 4, plus the number of items, which on this example is 6, so 4 plus 6, if that equals the size of the array, so 4 plus 6 is 10, if that equals the size of the array, which in this example was 10, I built this example to demonstrate this. If 4 plus 6, front plus the number of items, equals the size of the array, that means that the next item is going to have to go at index 0. which is precisely what we see right here. The new NQ position must be index 0, and so we will save that new value at index 0. But else, if front plus the number of items does not equal the size of the array, then we simply will NQ the next value at the next position available by incrementing. So consider right now that we have 7 items. Front is 4, plus 7 is 11. Is 11 equal to the Q dot length? It is not. So therefore, where do we insert the next item? We just increment rear and we insert right here. It's that simple. Or there is no rear, you're simply going to increment, you're going to insert at front plus the number of items, but again, taking care of wraparound. Let's look at the code. So here, if front plus num items equals Q dot length, the value is going to get saved at index 0 because index 0 is now where we're going to be saving that new value. But else, the value is going to get saved where? It's going to get saved at front plus num items. So this code looks like it works pretty nicely, except what about when we're now wrapping around? It still doesn't work. It only takes care of the situation when we've reached the end and we have to come insert the value at index 0. But what about right now when we have 7 items and front is 4? 4 plus 7 would be index 11. Clearly, we can't save value at index 11, so we need a bit more, which is where we come to the idea of using mod. So we know that the next NQ will go at index 0. How do we do this using mod? Once again, it's funky, but just check this out. If we can take that value and save it at this index right here, which is front, plus num items, mod the length of the queue. So let's look at this exact example, right? What we have right here. 4 plus 6, we want to save this G. Remember, we want to save this G at index 0. So 4 plus 6 is 10. Mod the length of the queue, which is 10, which will give us 0, and that's exactly where we save that new value. Let's pretend now we want to add a new value, W. We want to insert W now. Well, how many items do we have in our queue? We have 7. So we would say Q at save this new value W at which index? Let me come over here to the tab. We would get our Q at index front, which is 4, plus num items is 7, mod 10. And we want to save, let's say we said we want to save a W into that. This is the front, the 4. The num items is the 7. So we end up with 11 mod 10. And that's the index we want to save it into. Well, 11 mod 10, which means 11 divided by 10, what is the remainder? And we're now going to get a remainder of 1, and that is precisely what we want inserting this next value at index 1. Super cool that we're able to use mod to take care of that for us. So check out the final NQ code for this array-based version of a queue. We want to insert this value. Where does the value go? It goes at this index right here, which is front plus num items, mod the length of the queue. That will give you the index taking care of wraparound, and then simply you increment the number of items. We are at, I say the midpoint, you got about 5 to 10 more minutes. Is it funny? We've all had this happen though, right? You have a bug in your code, you're like, I'm tapping out, I'm going to bed. And as you're falling asleep, like, hey, wait, are you sleeping? You're like, no, shut up. And then the idea comes to you, or the solution comes to you. But that's better than the solution not coming to you. Last thing we're going to talk about is implementation of a queue using a linked list in Java. We want to implement this queue as a linked list. Once again, what does it mean? It means if we look under the hood, we're going to actually see linked list code. And what makes that linked list ultimately become a queue? The behavior. The fact that we're going to restrict what we can do with that linked list. We're no longer going to insert anywhere or delete from anywhere of the linked list. Instead, we want to make this linked list behave like a queue. So we're only going to allow insertions at the back of the linked lists. That's going to be our enqueue. We're only going to allow deletions from the front of our linked list, and that is going to be the dequeue. Deleting from the front, that's pretty easy. Just update front. Front equals front.next. We've now deleted it. Of course, you needed to save it temporarily first, but that's how easy deleting from the front of a linked list is, right? Well, that's your dequeue. What about inserting at the back? There's some considerations to be made there. You could traverse all the way over and then insert, but that would make insertion a time-consuming operation. So we want to insert at the back of our linked list, but we don't want to have to traverse every time, which means we need to always maintain a pointer pointing to that last node of our linked list. So what we need to do now is simply build this linked list class up to take care of our queues. We need to have a front, we need to have a rear or that back. Where do you want the front of the queue to be? Do you want it to be the head of the list, or do you want it to be the tail? You could actually have it be the tail, but in this case, it makes sense. Although the choice is yours, it makes sense that the front would be the head of our list, and the rear will simply be the last node of our list. And remember that the front of the queue is therefore going to be the head, so a dequeue operation is simply as what I've already stated. We're just making head point to that next node. It is super easy. Front equals front.getNext, and we have just done a dequeue operation. We need to first, before doing this front equals front.getNext, we need to first get a temporary pointer pointing to where front points to, because we don't want to lose that node. Then we say front equals front.getNext, and then we return that node, and that's it. Dequeuing is super easy. We're going to cover the actual method in its entirety in just a moment. Enqueue. How will you enqueue the next item into this queue? Because you need to know where is that last item. So as I mentioned, we could traverse each and every single time and then enqueue, but that would be an O of N operation for enqueue. Due to that traversal, that would be super slow. If the list was huge, that would be a fail. A better solution is we use this back pointer or end or tail, whatever you want to call it, right? To get to the back of your queue, we always maintain where is the location of the last node in our queue. So we're going to have this QLL.java class, which has now two important variables. It has a front variable and it has a back variable. And both of these variables need to be updated whenever we're doing enqueue and dequeue operations. The code is going to be fully on GitHub, which I'm going to link to for you. An enqueue is simply inserting into the back of our linked list. And this is going to be easy, no traversal necessary, because we're always going to know where is that exact location of that last node, and we're going to have a variable called rear that is pointing to that last node. So in order to simply do an enqueue, it's just changing two references, right? And a dequeue would be deleting that front node. This is the easiest type of deletion. Deleting that first node, once again, only changing two references. So in fact, a linked list version of a queue is easier to code than a regular linked list. Each node will be an element of the queue. Each node, of course, has data values, has a next. We're going to simply enqueue, inserting at the back, and we're going to dequeue, deleting from the front. Let's look at both of these classes, this QNode.java and the QLinkedList.java. Here's the QNode. We have a data and we have a next. Here, data is just 0 in the constructor, next equal to null. Here's our two constructors or more constructors. This is identical to the linked list code that we have seen previously. And we have some getters and some setters. Here is the class for the actual linked list version of our queue. So we have the two data members mentioned. We have front and we have back. If you want to call it end, you want to call it rear, all of that's fine. I've called it front and back right here. We have our constructor at the beginning. When we make a queue, it's empty, right? So both front and back are going to point to null. And of course, what follows are many other methods for our queue, enqueue, dequeue, not push and pop. That would be for a stack. So here's our dequeue method. Let's understand this method. That's all that's left. Understand the dequeue method, understand the enqueue method. So remember, dequeue is what? We're removing the first element in that queue. So ultimately, this is what's happening. How do you officially do the dequeue? Is front can no longer point to the first node. Front needs to point to that second node. It has then been removed from the queue. So front equals front.getNext. Of course, before you do that, though, we don't want to lose that first node because when we dequeue it, maybe you want to dequeue it and do something with it. Maybe you want to put it into another line, right? So before you dequeue it, we first want to save the address of whatever's in front, that previous first node, save it off temporarily into a variable. Here I call it temp. So we have queue node temp equals front. So temp is pointing to the exact same node that front is pointing to, the first node in the queue. But now we update front, and front no longer points to that first node. Front now points to the second node, which is the new first node. And we've taken that first node, and we're going to then return it. We saved it into temp, and we're returning temp. But after we update front, though, pay attention to what happens here. If by updating front resulted in the fact that the queue was empty, because imagine there was only one node in the queue. If front was pointing to one node and it was the only node in the queue, well, after we do this line of code, front will now be pointing to null, right? So if front is null, you have to make sure to set back also equal to null, indicating that the front and the back both are pointing to null. But that's the dequeue. It's super simple. It's really front equals front.getNext. That takes care of the dequeue in and of itself. It's removed it from the queue, but ultimately you need to return that node, which meant you first had to save a temporary variable, have that temporary variable storing an address to that previous first node, and then return it off. That is your dequeue. Your enqueue method. Let's look at this one. We want to enqueue a new value into our queue at the back of the queue, right? Well, the first thing is we make a new queue node with that data value, and we save it into this variable temp. So now we need to check, hey, is the queue empty? If the queue is empty, this new node is going to become both the front and the back. Let's make sense of that. Let's come over to the actual tablet. And here, if we have front pointing to null and we have back pointing to null, but now we want to enqueue a new item. We'll make a new item. Let's say it has the value 18. And when we make this, the next is by default pointing to null. And so now this new item is going to become both the first item in the queue and the last item in the queue. So this is going to get erased. And now front is going to point over to this new node 18. Back will point over to this new node 18 as well. So if the queue is empty, we're going to take this new node, we're going to save its address into back, and we're also going to save that exact address into front. You could have said front equals temp, and then on the next line said back equals temp, or just front equals back equals temp. Works just fine. But else the queue is not empty. If the queue is not empty, what actually needs to happen? Let's go back over to the tablet. Let's pretend the queue is not empty, in which case I'm going to come over here and just drag this. And let's say right now we want to enqueue yet another item. We want to come over here and enqueue, here's a new item. We're going to enqueue 25. So we make this new item 25. It points to null. Well, if it needs to get enqueued, it needs to come after the 18. So think about how we would make that happen. If 25 comes after the 18, that means that we need to somehow make a connection right here. We need to make the next of 18 point over to 25. And because there's only one node in the list, you might be thinking that you could do that with the front or the back, and you'd be correct. But let's pretend there was 30 nodes in the list. We would want to do this via the back reference pointer, right? So let me actually erase what's here so we can make it even super clear. And what if, instead of all of that, what if we have many nodes, right? We have all these nodes that are in our queue. Pretend they're all linked together. And here we have that last node, and back is pointing to this last node. And now we're trying to insert a new node into this queue. Let's say this was 18 and this is 25. And back was currently pointing to null, right? Because it was the last node of the queue. But now we want to insert this new node 25. How do we do that? Well, we're going to make this new node. And let's say, remember, we had this new node, we have it saved into a variable called temp. So what we're going to do is we're going to take the address of this new node, which is stored inside this variable temp, and we're going to save that address of this new node into the next of node 18. So how do you actually make that happen in code? We would say back dot set next to temp. It's that simple. Set the next of back, which is this right here. Set that next to temp, which means that back, the next of 18 will point directly to temp. That's it. Now we've inserted this, we've enqueued this new node into our list, but before we finish, we need to update where back points to, because back is currently, after we've now enqueued that, back is pointing to the second to last node. We need back to point over to here. So how do we simply change where back points to? We're experts at that. How do we step one node down our list? Help pointer equals help pointer dot next. Here you'd say back equals back dot next, or back equals back dot get next. And this is the exact 2 lines of code to make that happen. Look, we're over 50 minutes. This is a long video, a lot of content, understanding the array-based queue, really the nuances of that circular option, that circular implementation, the usage of mod for both enqueue and for dequeue, a lot to really wrap your mind around. It will help clarify when we get to see examples when we meet together. Also here with the linked list based implementation, it'll make a lot more sense when we go over the code in its entirety with a full code breakdown of this. But the code's currently going to be available at GitHub. I encourage you to check it out and play with it. Try to make sense. This has been fun. As always, reach out, ask if you have any questions. And I'm jumping ahead. I'm forgetting my demotivator. A company that will go to the ends of the earth for its people will find that I can hire them for about 10% the cost of Americans. Maybe it's not the funniest one. Just came from despair.com. Like it, don't like it. It's okay. Take care, everyone.